Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp 2, Lecture 9 on Simpson's paradox and confounding. In this lecture, we're going to talk about a phenomenon called Simpson's paradox. I don't find it to be a paradox, but it's called Simpson's paradox. We'll talk about some examples like the Berkeley data of Simpson's paradox, and then we'll talk about this related to the treatment of confounding. And then I want to cover a particular way to handle confounding through weighted estimators, and then talk a little bit about the Cochran-Mantel-Haenszel estimator. Okay, so consider this data right here, which is taken from Agreste's categorical data analysis book. I think I've mentioned this book in the past. In this instance, there was a cross-classification of defendants from criminal trials where they cross-classified by the race of the victim. These are all murder trials, so the race of the victim versus the race of the defendant, and then whether or not the person got the death penalty. And here I present all of the possible cells plus all the possible marginals. So for example, here you see the 8 cells that classify victim's race, and here we're only factoring in 2 race denominations, white and black, and death penalty, so there's 8 cells. And then here I have the margin for the defendant, white versus black, summed over victim's race, and then here I have the victim, white versus black, summed over the defendant's race. Okay, so let's actually investigate this. So we're looking at the percentage of people that got the death penalty. So if you look, white defendants received the death penalty a fewer percentage of the time, 11 to 22%, for both white victims and black victims. 0 of the white defendants received the death penalty for the black victims versus 2.8%. Okay? But then something kind of paradoxical occurs. If you disregard the race of the victim, it actually comes out that white defendants received the death penalty a greater percentage of the time, 11% to 8%. Okay? And then if you look at the race of the victim, disregarding the race of the defendant, actually in the instance where the victim was white, the defendant received the death penalty a higher percentage of the time, 12% to 2.5%. But let's forget this last 2, race of the victim, marginal, and let's just compare the table itself, in which case, in both cases, the white defendants got the death penalty a smaller percentage of the time than the black defendants, regardless of the race of the victim, versus the marginal here, 11 to 8%, where the white defendants got the death penalty a greater percentage of time than the black defendants. So what's happening? If you were asked to, this was related to a court case about whether or not the death penalty was being equally applied, and so what would you conclude? If you condition on the race of the victim, you get a totally different, the opposite answer than if you look at the race of the defendant disregarding the race of the victim. So what is the right answer? So let's just discuss a little bit about what's going on. So marginally, white defendants received the death penalty a greater percentage of time than black defendants. Across white and black victims, black defendants received the death penalty a greater percentage of time than white defendants. And Simpson's paradox refers to the fact that marginal conditional associations can be opposing. In this case, if you take the margin across victim's race, you get a different answer than if you condition on victim's race. Here, so here the death penalty was enacted more often for the murder of a white victim than of a black victim, and then whites tend to kill whites, just demographically, hence the larger marginal association. And I want to, kind of do a little bit of a commentary before I go through more of examples, so I'm going to cover several examples. First of all, when you state Simpson's paradox in the following way, it doesn't seem that paradoxical at all. And the paradox is the apparent relationship between 2 variables can change when factoring in a third variable. And then that seems obvious. Of course that's true. It just seems difficult when you start to get mired in the specifics. And later on I'll go through the math to say that there's nothing paradoxical about the mathematics of Simpson's paradox. Larry Wasserman on his blog, The Normal Deviate, has the most wonderful discussion of why Simpson's paradox is difficult and what the mistake people are making. And the mistake people are making is they're equating the statements, the causal statements, with the probabilistic statements. And the probabilistic statements can be misleading and paradoxical, and you're trying to make difficult conclusions in the light of noisy evidence. And in addition, even if you knew the exact probabilities, the probabilities themselves can exhibit the paradox. However, the causal statements cannot exhibit a paradox. Okay, so the problem, I think, his statement is that the real confusion is equating the cause. In this case, if you were, the cause would be, you would say that, for example, juries tend to causally convict black defendants more often than they convict white defendants. If you were to make that causal statement, then it is impossible for marginal and conditional causal statements to disagree. And so, the real details of this, I'll put up the link to his blog post, which is wonderful. But the real details of investigating the causal statements is beyond the scope of this class. We're not going to cover causal inference in this class. But I think it was a great discussion on his part to basically show or demonstrate that it is this conflation of cause with describing probabilities and associations that is the apparent paradox. But mathematically, there is no paradox, and I think when we go through it, you'll see. So here's another example that was on Wikipedia, which is a wonderful example. It's kind of a famous example in this area, just to describe the numbers, how this numerically can happen. So in American baseball, a batting average, so if you've never seen or heard of baseball, baseball's a game where a player, look it up, a player goes up with a bat and the pitcher throws the ball really hard. It's really, really quite difficult to hit a baseball, especially in the professional leagues. They throw the ball 100 miles an hour. So the player swings the bat and tries to hit the ball. The percentage of, basically, not exactly, but the percentage of time that the player hits the ball is going to be their so-called batting average, right? And really good players can do this, let's say 30% of the time. Excellent players, but most players are worse than that. Okay, so here's two players and their batting average. So player 1 had 10 at-bats in the first half of the season and got 4 hits. Player 2 had 100 at-bats and got 35 hits. So player 1's batting average was 40%, player 2's batting average was 35%. The second half of the season, player 1 got 25 hits out of 100, 25% batting average. The second half of the season, player 2 got 2 out of 10 hits, 20% batting average. So in both the first half and the second half of the season, player 1 had a better batting average than player 2. Right? However, if you just add up these numbers, 29 hits out of 110 at-bats for the whole season for player 1, and 37 at-bats for 110 for the whole season for player 2, you get 26% for player 1 and 34% for player 2. So player 2 has a better batting average. So it seems paradoxical that a person can have a better batting average for both the first half and the second half of the season, but have a worse batting average overall. But of course, the numbers work out, right? You see it. The numbers actually work out. And so, I put in consider the number of at-bats here because that's coming into play. That the player 1s had this very good batting average when they had relatively few at-bats, and a modest batting average when they had lots of at-bats, and vice versa for the other players. So that's, I think, really the culprit in this case. Okay, and another very famous example of Simpson's paradox is the so-called Berkeley admissions data, and it's fun and it's in R, So I'll cover it a little bit, and you can explore it, because to get it, you can just do help UCB admissions, and then that'll describe the data set. Data UCB admissions will load it up, and then here I give a little command, apply UCB admissions C12 sum. It gets the appropriate marginal. So here we looked at whether or not, so for admission versus rejected by gender, and we get that males, the acceptance rate was higher for males than it was for females, disregarding everything else. Okay, but I give another command here, and then it shows now the admissions rate. I'm not showing the counts because the table is getting a little bit unwieldy. So I'm showing the admission rates by department A, B, C, D, E, F, and E and F. And then what you can see among, for Department A, males got admitted fewer percentage of the time. Department B, males got admitted fewer percentage of the time. Department C, males got, got admitted a slightly larger percentage, lower for D, slightly larger for E, and lower for F. So clearly the admissions, gender imbalance in the admissions is dependent on whether you're conditioning. The evidence of gender imbalance in admissions is dependent on whether or not you're conditioning on department. And there's different application rates, and you can explore this yourself. There's different application rates by gender for each of the departments. And so look here, in fact, you don't even have to explore it yourself. I apparently have it on here on the next slide. So gender, male, female by department, and you can, you can explore this a little bit more because the data is just in R. I don't think you have to have any other packages installed. You can just do data UCBA admissions and play around with it. So let me talk a little bit about what in the world is going on here, because it's confusing. It seems confusing. To me, there's a couple things that help me understand Simpson's paradox. First thing is the math. There's no problem with the math, right? If you're saying that A over B is less than C over D and E over F is less than G over H, but if you can find integers that satisfy the following equations, where B has to be greater than A and F has to be greater than E and so on, but if you can find integers that satisfy these equations, then you've found an example of Simpson's paradox. You just have to put the context around it. But it doesn't seem at all paradoxical when you state it as a couple of relationships between integers this way, right? Then it just doesn't seem very paradoxical anymore. It's the context that adds the paradox, and just from a statistical standpoint, it says the apparent relationship between two variables can change in the light or absence of a third, which again doesn't sound that paradoxical. It's only when we conflate the probabilistic statements and the evidence associated with the probabilistic statements vis-a-vis the data with the causal statements, right? So the problem is we're going to try and get at the cause, the truth, by virtue of the probabilistic statements and the associations obtained from the data. But that's a quite hard thing. The question in all these cases is, what's the right answer? What should you condition on, or should you not condition? And that's a hard problem. We're not going to really cover that in this class. To me, the real answer of this is that it's quite hard to exactly figure out when you've conditioned enough, right? And in some cases, no conditioning is exactly the right answer, and in some cases, conditioning is exactly the right answer. To really handle this formally, you've got to do something called causal inference, basically, and that is really the discipline that's really the subdiscipline of statistics that is really entirely designed towards addressing this question in a formal manner. In the meantime, but let me say this. In the meantime, what can you do? And the idea is to not decouple the statistics from the scientific discussion. in the case of the death penalty, you would want to, have a discussion about hypotheses for the causal mechanisms between the various associations. Does it make sense to be conditioning on the race of the victim? In the Berkeley admissions data, you'd want to talk about, well, are there very different acceptance rates by departments, and then are there different application rates by gender to each department? And does the fact that, say, are women applying to departments that are harder to get into? That would explain the marginal association quite well. And is that really the driver? And that's a discussion, kind of in a sense, a discussion that's informed by the statistics, but extra statistical. And at this point, I think it is this kind of interplay between the data and a scientific discussion is the best solution I can offer to you for dealing with confounding. When you take further statistical courses, you can learn some of the formal mechanisms for trying to account for confounding. But suffice it to say, it's one of the harder issues in statistics, knowing how to balance the over-adjustment with under-adjustment in terms of confounding is one of the central problems in observational data analysis. And it's what makes observational data analysis so hard compared to, say, for example, where you randomize a treatment or something like that. So I've been using the word confounder a lot in confounding, so let me define it. So variables that are correlated both with the explanatory and response variables are confounders, and they can distort an estimated effect. So in this case, victim's race was correlated with both the defendant's race and whether or not the death penalty was executed. This is a I think a kind of old school definition of confounding. There's a modern definition given by causal inference inference classes that I think you might be, if you're interested in the field of statistics, will be worth learning. I think ultimately with a confounder here, we haven't really distinguished between something that's causally related with the race and the death penalty versus something that has a statistical association with race and death penalty. In this class, we're mostly going to be talking about things that have a statistical association with the explanatory and response variables, where there is kind of a plausible causal connection between them. Okay, so again, putting aside the rather difficult and lengthy discussion of what is a confounder, how do we select our confounders, how do we, that discussion, putting it to the side, let's assume we have a single confounder. How do we adjust for it? Well, there's several ways. Regression is probably the biggest and most common way to adjust for confounders. But kind of an old school way in categorical data analysis is to stratify by the confounder and then combine the straightest specific estimates. And so this requires appropriate weighting of the straightest specific estimates. And we'll talk in a minute about how do you do the appropriate weighting. And unnecessary stratification has its own set of problems. So, again, just bringing back this discussion, the solution to the confounding problem is not just to stratify or adjust for everything in sight, right? That's not the solution, because that has its own host of consequences. For example, in any of these Simpson's paradox examples, imagine you had a giant database and you were interested in, say, the death penalty, and you had a giant database with lots of other variables. For sure, you could find one variable that reverses the association but has no bearing on whether or not a person received the death penalty, right? So adjusting that for that confounder will reverse the association but has no business being adjusted for. And so it's a hard topic. Admittedly, it's a hard topic of selecting confounders and achieving balance between the right amount of confounder adjustment and the with over adjustment, balancing between that and over adjustment. So let's stipulate for the time being we have a confounder, we want to adjust for it, and what I really want to talk about is the method of stratifying and then combining straightest specific estimates, and because then we'll be able to teach you some nice methodology, and then as you take more statistics courses, you'll learn more about the delicate surgery of dealing with statistical confounding. Okay, so here I have an aside, but it's an important aside. Suppose you have two scales, and what I mean by scales, I mean things for weighing objects. And let's assume both the scales are so-called unbiased. They both have some variance associated with them. If you weigh the same thing over and over again, you get different answers. But one has a variance of 1 pound, and the other has a variance of 9 pounds. They're both unbiased. Confronted with weights from both scales, would you give both measurements equal credence? So let's just suppose we weighed an object, and that our first weight was this variable x1, and we're going to assume that its normal, mu, and the variance of the first scale, sigma 1 squared, and then x2, because both scales are unbiased, we're going to assume that it's normal and it has the same population mean, mu, and the same, a different variance, sigma 2 squared. And let's assume both sigma 1 and sigma 2 are known. We want to estimate mu, this unknown weight of the object. Okay, so we measured it with one scale with one precision, another scale with another precision. We're assuming both scales are unbiased in that if we measured the same object over and over and over again, the average would be about right. If we characterize this in this way, I'm hoping what everyone can do in the class is set up the likelihood, multiply the two, add the two log likelihoods or multiply the two log likelihoods and take the log, and then come up with the fact that the log likelihood for mu, disregard any terms that don't involve mu, and I'm hoping everyone can come up with the fact that the log likelihood for mu looks like this, bottom equation right here. Okay, and let's solve for a maximum likelihood estimate. So the easiest way to do that right now would be to take the derivatives, set the derivative equal to 0, and you get this answer, x1 times r1 plus x2 times r2 divided by r1 plus r2, or in other words, x times p plus x2 times 1 minus p, where p is r1 over r1 plus r2, and 1 minus p is r2 over r1 plus r2. And then in this case, ri is 1 over sigma squared sub I, and then p is, of course, 1 over r1 divided by r1 plus r2. So why does this make sense? This makes a lot of sense to me now. But the first time you see it, you might say, this makes no sense. But let me describe why this makes a ton of sense. Okay, so notice what each Ri is. It's 1 over the variance. So if, let's say, sigma 1 is huge, in other words, that scale stinks, it has this huge variance, then the weight, R1 times X1, the weight given to the measurement from that scale is very low. And then conversely, if sigma 2 is very small, then I get R1, which is 1 over sigma squared, will be a huge number, and then X2 is given a gigantic weight. And then we divide by R1 plus R2 so that when we weight these two things, X1 and X2, we get a convex combination, P times X1 plus 1 minus P times X2, so that it's an average. It's just a weighted average. Okay? And by the way, you can do this always. If you want to take a generalized form of average, right, and you want R1 is the weight for X1 and R2 is the weight for X2, they have to be positive, of course, and you want to turn it into an average, then just divide the whole thing by R1 plus R2, and then you'll turn it into P times 1 and 1 minus P times the other. If R1 equals R2, they'll be the strict arithmetic average of the two numbers. If R1's different from R2, it'll weight one of the observations more than the other. Well, the answer in this case is that we want to weight by the inverse of the variance, giving high variance measurements low weight and low variance measurements high weight, which to me then makes a ton of sense. Okay, so at any rate, the general principle, instead of averaging over several unbiased estimates, take an average weighted according to the inverse of the variances. And this is so ingrained in statistical practice now that people do it without thinking. They don't go through this exercise of deriving maximum likelihood equations. So in our case, sigma 1 squared was 1, sigma 2 squared was 9. So in this case, you can work it out. P works out to be 0.9. So it works out to be 0.9 times the first measurement plus 0.1 times the second measurement. The first measurement getting a lot more weight because the scale, has 1/9 the variance of the other one. So there's a great example of this. Imagine just going back to our death penalty example. And here we had two 2-by-2 tables. We had the defendant's race and whether or not they got the death penalty. And then we stratified that by a third variable, victim's race. So let Nijk be the ijk entry of table K. So in this case, K equals 1 to 2. K equal 1 would be the first victim's race. K equal 2 would be the second victim's race. And then I and J would index defendant's race and whether or not the person got the death penalty. So in our first example, we had two 2-by tables stacked one on top of the other. K indexes the first one, K equal 1 indexes the first one, K equal 2 indexed the second one, and then Nij indexed the individual elements of that 2-by-2 table. So then the kth odds ratio, the kth sample odds ratio, so remember the odds ratio was the cross product ratio, so the main diagonal divided by the off diagonal, so n11 times n22 divided by n12 times n21. So in this case, everything indexed by k, referencing the kth table. So the kth sample odds ratio is sigma hat sub k. Then the Mantel-Haenszel estimator is exactly our weighted average of these stratus-specific estimates. It's summation weight rk times theta hat sub k divided by the sum of the rk's. And by the way, when we had two, it was r1 times x1 plus r2 times x2 divided by r1 plus r2. But if we had 3, it would be r1 times x1 plus r2 times x2 plus r3 times x3 divided by the sum of the r's. And if we had 4, same thing. Anyway, this is the Mantel-Haenszel estimate. This is the sum of the weights times the stratus-specific odds ratios, theta hat sub k, divided by the sum of the weights. So we just get a weighted average, a simplicial convex combination of the stratus-specific odds ratios. And then what are the weights? Well, okay, so the weights in this case are this little formula right here, and I'll describe where they come from. But the motivation for the weights is that they're inverse variances. That's 100% the motivation for the weights. They're inverse variances from a hypergeometric distribution. So you can just think of, we're exactly doing the same thing we did with the scales, only now in terms of the odds ratio. And then anyway, this simplifies the so-called Mantel-Haenszel estimator. Here's the formula right here. I would suggest that you look in Agreste's book, page 235, in the version I was looking at, but you can look it up. The version's probably changed. Rosner's book, which is very comprehensive, page 656. They give the standard error. It's a long formula. I'm sure you can find it on the internet as well. This is the so-called Mantel-Haenszel estimator, named after the two great epidemiologists, Mantel and Haenszel. Okay, so here's an example, and here's a great example of this Mantel-Haenszel estimator. So here we had an active drug, T, and C being a placebo control, I guess. And then here we had success versus failure. And I'm going to abstract what the specifics were of the experiment. And then what people were concerned about was whatever policies and practices existed at the various centers in which the data were collected. So they stratified by center. 1, 2, 3, 4, 5, 6, 7, 8 centers. So they got 8 odds ratios, right? And they were worried that the center was a confounded. There's several reasons actually you might want to do the Mantel-Haenszel estimator in this case. But let's talk about it in terms of confounding first. So imagine if you thought that the center was specifically associated with the treatment application. Some centers tended to apply the treatment more than others, and that the center was associated with the success of the treatment because of different policies associated with the center and how the treatment was delivered or something like that. Then you would want to adjust for the center as a potential confounder. And then here you would, and we're going to adjust for this confounder by stratifying by center, getting an odds ratio specific to every center, and then averaging over the odds ratio, but factoring in the inverse variance of the odds ratio. Some centers have more patients, right? This one had 73, this one had 14, so we want to weight the one with, say, 73 more than the one with 14 because they have a better, more precise odds ratio. And so that's what the Mantel-Haenszel does. And so you get this, you get an odds ratio of 2.13. The log odds ratio is 0.758, and the standard error, because of the standard error calculation, it uses a delta method type argument. Standard error of the log odds ratio works out to be 0.303. You would take 0.758, add and subtract, say, 2 standard errors, and exponentiate the endpoints to get a confidence interval for the odds ratio. Let me talk a little bit about the another rationale for why we might want to do some sort of stratified estimate. It's also often the case, in this case, we think that center is at some level this random effect type modifier of the treatment of efficacy. And we are willing to think of these centers as sort of a random draw from the population of centers. Then in that case, it still actually makes a lot of sense to combine them, because we're not so much interested in center-specific effects. We don't care if the treatment works at center number 1. What we care is if it works overall. And it turns out, even if the center isn't just a confounder, but it really modifies the effect of the treatment, then some places are just better at doing the treatment than the others. Then really kind of what you but if you're willing to make the assumption that the centers are this sort of random draw from a population of centers, then this CMH estimate makes a lot of sense, saying, okay, averaging across centers, here's the effect of the treatment. And that's another instance where you would consider doing something like a Mantel-Haenszel log common odds ratio estimate. So this is what is often called as the common odds ratio across centers. So then there's a famous test for testing whether or not the odds ratios are the common odds ratios are equal to 1. So the test is usually stated as the null hypothesis that all of the stratus-specific odds ratios are equal and they happen to be equal to 1, versus the alternative. And there's some amount of dispute over the alternative, but I'm going to teach the alternative this way. The alternative is that they're all equal, right, but they're not equal to 1. Okay? So notice this is different than the alternative that they're not necessarily equal even. So here we're assuming that we have a common odds ratio under the null and alternative, and we just want to test whether that common across strata odds ratio is 1 versus not. And it turns out that the CMH test applies to other alternatives, but it's more powerful for the particular alternative given above. I'll also mention that this test is exactly the same as testing for conditional independence of response and exposure given the stratifying variable. And so this Cochran-Mantel-Haenszel test, the way it's executed is it conditions on the rows and the columns for each of the contingency tables exactly like Fisher's exact test, resulting in hypergeometric decay, hypergeometric distributions, and then leaving only the upper left-hand cell of each table free, just exactly like we did in Fisher's exact test, only this time doing it for each specific cell. So I'll go through the mechanics now. Okay, so under this conditioning and under the null hypothesis, under both those circumstances, then the expected value of the upper left-hand cell of each table is this value. The variance of the upper left-hand cell is this value. So the Cochran-Mantel-Haenszel test statistic works out to be this guy right here, kind of the sum of the deviations of the upper left-hand cells from their expected values but summed up and then squared, unlike the chi-square test where they're squared and then summed up. So summed up and then squared. And then regardless of how many tables you have, under the null hypothesis, this is a chi-squared 1. Remember, this is a different test than the chi-square testing we talked about in the previous lecture, so that's why it's a different test statistic. And the idea of testing conditional independence or testing for this confounder relationship is a different idea, and that's why you get a different test statistic. I think it's a little bit beyond the scope of this class to derive the CMH test statistic. But the idea is here you want to test for whether or not the odds ratio is 1, given that it's common across all strata, versus the odds ratio, given that it's common across all strata, is not 1. So here I'm going to implement it. It's a bit of a pain to actually execute the CMH test by hand. So here I'm putting the data into an array. In this case, 8 2x2 tables, and then you can do this Mantel-Haenszel test. Correct equals false. I put again correct equals false here so that if you do the calculations by hand, you'll get an agreeing result to the R output. You generally want to leave this correct equals true. The result is the test statistic is 6.38. Compare that to a chi-squared 1 value, or again, you only reject for larger values of the test statistic. Again, it being a two-sided test because it's a squared statistic. And so in this case, the p-value is 0.012, so the test presents evidence to suggest that the treatment and response are not conditionally independent given center. Some final notes on this testing is, it's possible to perform an analogous test using a kind of what I consider to be a little bit more modern of approach, using a random effects logit model. And the reason I like, but again, we're not, we haven't covered regression, so we can't cover mixed models, and then we can't cover generalized linear mixed models and all the machinery that you would need to cover this. It's possible, at any rate, I think you should take the time, if you're going to work as a statistician or use a lot of statistics in your life, you should take the time to build your way up to where you're studying mixed effect models and generalized linear mixed effect models. And there you can do exactly things like what the CMH test is doing, only you can do it in a very general way that allows for other variables to be specified in the model and so on. The reason for presenting it this way in this class is to just give you a sense about the idea of confounding, to give you a sense of what you can do just in particular in the case of 2x2 tables. And then later on, I'm hoping that you'll take some more statistics classes and learn about mixed models and generalized linear mixed models. It's also, so here we assumed all the odds ratios were equal versus the alternative that they were all equal but not equal to 1. It's also possible to test whether or not all the odds ratios are equal. There's a test for that. I think it's called Wolf's test. That's a very good test. I don't have time to cover it. The final thing I would mention also is that we have these K hypergeometric distributions that we used in the CMH test statistic. So you can probably guess that you can exactly do some sort of exact test in this case. And you can, in R, you can just do exact equals true as an argument in the Mantel-Haenszel test. But you could probably envision how it's done. Imagine is within each center, you were to permute do this permutation process that we talked about for Fisher's exact test. Imagine if you were to do that now within each strata, then recreate the chi-squared statistic each time, the Mantel-Haenszel chi-squared statistic each time, and do that over and over and over again, and that simulation would yield an exact p-value. So I think you could actually probably come pretty close to doing exactly what the exact equals true argument is doing in R by that permutation process. Of course, in this case, they can do the calculations exactly without Monte Carlo. So it's faster, but conceptually, that's exactly what they're doing. Okay, well, that's the end of the lecture. And so anyway, this was a teaser on the idea of confounding. And confounding is, I mean, one of probably the biggest obstacle to generating knowledge from observational data, data where you don't have a heavy amount of control over the design of the experiment, which is most data, right? The easy data to collect is observational data. So this gives you a teaser in how that data is collected, how that data is analyzed, and there's a tremendous art to analyzing that data that I hope as you learn more statistics you'll get more refined at that art. And just like any other art, you can spend a lifetime perfecting your craft and you'll never really hit a limit. It's a very hard topic. And then again, I highly recommend considering learning something about causal inference, which is the most modern attempt at addressing this problem in a mathematically formal way.